Hi everyone. So today we're still doing differential equations, and this is lecture 6, and today we'll specifically look at equations reducible to exact equations. So we previously looked at, in lecture 5 we looked at the exact equations, and now we have to see how if for instance we've been given an equation which is not exact, how you can reduce it to an exact equation by using what are called integrating factors. And then here what you can see here is just this statement here. First I start with this statement here. It's just the format of exact equations, and then this this other statement, the second one here, is just telling you to say if dm dy is not equal to dn dx, the partial derivatives of this, then the equation is not exact, and hence we resort to what is called the integrating factor, which is just e raised to power the integral of fx dx. So the integrating factors differ depending with what we're going to look at. So what is an integrating factor? You need to know what an integrating factor before you even start doing anything. So an integrating factor is just a function of x and y, which when multiplied with a differential equation will make it exact. So in other words, when you multiply a differential equation by an exact, by an integrating factor, you get an exact differential equation. So that's if a differential equation is not exact, it may be possible to make it exact by multiplying it by an integrating factor. So for instance, when you have this question here, this question, when you test it the way we were testing, whether if you want to know, or if you want to tell whether the differential equation is either exact or not, if we test it, you discover to say it's not exact. How do I know? You can try to find, we know to say this function here is m, and then this function here is n, and then when we find the partial derivative of m with respect to y, you discover that this is going to give you, when you differentiate this, you just get 1, and then when you differentiate this part with respect to x, when you find the n dx, you discover that the answer that you get here will just be a constant 2. So when you look at these two, they are different. So in other words, dm, the partial derivative of m with respect to y, is not equal to the partial derivative of n with respect to x. So if you discover that dm dy is not equal to dn dx, then the given function, rather differential equation, is not exact. Now how can you make it exact? You find a certain number, or rather you can find a certain function that when you multiply it with this whole function here, this equation will become exact. Yeah, so let's try to see what I'm talking about. So after finding that, we discovered to say dm dy is not equal to dn dx. As a result, the equation is not exact. But if the equation is multiplied through by y, we're going to get equation 2, which is this one. So this equation will therefore be exact. You can try to differentiate this. When you find when you find the partial derivative of m with respect to y, you get your solution to be, this will be 2y. And then when you find the partial derivative of let me just write it properly. Then when you find the partial derivative of n, sorry, not m but n, and then the partial derivative of n with respect to x will also give you 2y. So because we're going to differentiate this with respect to x, you get 2y. So you can see that dm dy, which is this part, is just equal to that part. Hence the equation is exact. So this y which we have multiplied through this equation is what is called the integrating factor, because after multiplying this y with this equation, we we had this equation become exact. So that is what we mean when we talk about an integrating factor. So after multiplying with y, you can see that dm dy is equal to dn dx, and this means that y is an integrating factor for the given differential equation. Alright, so you should also note that integrating factors may also be found by visual inspection after regrouping the terms involved in the equation. So like what we did here in this first example here, we just used inspection, where you just observe, you group the terms, and then you see which function you can multiply with a given differential equation to make that exact. So what we used here was just inspection. However, there are other methods. There is a general method that you can use to find these integrating factors. Let's take a look at this method. So these are the rules now that you are going to use to find the integrating factor for a non-exact differential equation if you want to make it exact. So the first rule is form the equation. So meaning arrange the equation, let it be in this format. So when your equation is in this format, you quickly now integrate, integrating factor of the differential equation, which is this equation, is now given by this, it's given by that. So now, how do we find f of x? What is this f of x? So how do you find this f of x? So f of x is just given by 1 over n. So you just say 1 divided by n. Our n is just this part. So you say 1 divided by n, and then you multiply with dm dy minus dn dx. So and this only works when the function and this is only valid for functions of x only. That's all. So what do you mean when you say this is valid for functions of x only? So when you find the equation here after finding the f of x, you discover to say f of x is just a function of x. It does not contain y anywhere. That's when you are going to use this integration factor, this formula for the integration factor. And then if there is y, you just switch these two. You start with dm dy and then the dn dx. So you start with dn dx and then dm dy. So in other words, when you switch these two, if for instance the function that you find here after simplifying these two, you find a function only contains y, meaning this. In other words, if you don't want to switch this, means that you just have to add a negative outside there, which is just the same as what I'm talking about. So you can either add a negative outside or you just switch these two. Okay. So let's see what I'm trying to talk about. So integrating factors of differential equations. This equation is given by this. So you add a negative outside when this function is a function of y only. Yeah. So this is what normally happens. So let's quickly apply now the methods that I've shown you, the two methods I've shown you to find the integration factors. Let's apply them and see what we can do. So I have about 2 examples that we're going to do, applying the 2 methods that I've shown you. So the first example is this one, which says x squared plus y squared plus x dx plus xy dy is equal to 0. So if you have this function as a differential equation, then you can test it if you want to know whether it's exact or not. So you can test it by finding find the partial derivative of m with respect to x. So when you find this with respect to x, you're going to have 2x, there's an equal sign here, you're going to have 2x, and then this is a constant, meaning it will just go. We'll consider this as a constant because we're differentiating it with respect to x, and then we say x there will become 1. Same applies when you find here, you find the derivative of this with respect to sorry, I made a mistake here. I'm supposed to find the m dy, and then I'm supposed to find the n dx here. Yeah, so the m dy is not supposed to be this, it's supposed to be just 2y. And then here the n dx is just going to give me y. So now you see that the m dy is not equal to the n dx. As a result, what we're going to do is we need to find the integrating factor that when we multiply it through this equation, we're going to make this equation exact, meaning the m dy is going to be equal to the n dx. So let's quickly see what follows. So that the solution, now we identify which one is our m and which one is our n. So when you find the m dy and the n dx, you discover to say they are not going to be equal. So what do? We find a suitable method now. So this is the formula. Yeah, so you can see this is the formula that I'm just from explaining on the previous page. I say 1 over n plus 1 over n times the m dy minus the n dx. So 1 over n, which one is our n? Our n is just xy. So you say 1 over xy is 1 over xy times, and then what is the m dy? The m dy you get 2y, and then minus the n dx, which is just y. So after simplifying this, you can see that that y will go with that, so meaning just remain with 1 over x. So now this is the part where I was saying if the function that you find only contains x, it has no y, then you use then you take this method to be positive. When it only consists of y and then it doesn't have x, then you take this method to be a negative. This expression to be negative. What do I mean? Meaning when writing the integrating factor, the power of e here is supposed to be positive. Yeah, so when you integrate 1 over x, you just get ln x, then this ln x and that e will cancel. As a result, you just remain with x as the integrating factor. So you multiply this x throughout this equation. So when you multiply this x with throughout this equation, you are going to get this function. So you're going to get this function. So after getting that function, you can see that now after differentiating the two terms here, you find the m dy and the n dx, you find that you're going to have same answers. So the m dy, let me just write it this side. What is the m dy from this? If we get this as our n, our m. So the m dy here will just be 2xy. We get 2xy, and then our n dx. The n dx here, when we differentiate this, we still get 2xy, which proves that our integrating factor is correct because we've gotten the same answers here on the m dy and the n dx. We've gotten the same answers. So let's quickly now move on to the solution. So this is the general solution. Yeah, this is the general solution. How do you find this general solution? Check the previous lecture. Yeah, I explained how you find the general solution. So how do you find, let me just maybe talk about it briefly. How do you find the general solution? So you are going to integrate this with respect to x, and then here you only integrate the terms that in this part you only integrate the terms that only contains y, but since we have this term and it contains both x and y, so meaning we just leave it, we just cancel this and then just focus on that. So when you integrate the first part there, you get that. Integrate this second part, you get that. Integrate this part, you get that. And then integrate the zero, you get the constant k. Alright, so let's quickly, or if you want you can simplify it further to that format, which is just okay. Let's quickly move on to the next question. So our b, so this b is also a question, it's also an example which is going to apply the second method that I showed you, where you discover to say the final answer that you get after finding the function only contain the function, or it's only going to be a function of y. So what do we do first? Let's try to find dm dy and then dn dx. We see if they are going to be equal. So when we find dm, the partial derivative of m with respect to y, you discover to say you just get 1. And then when you find the partial derivative of n with respect to x, you find the partial derivative of n with respect to x, you get your solution to be just a 3. And when you look at these two solutions, they are totally different. Now how do we make this expression exact? So since dm dy is not equal to dn dx, then we know to say this expression is not exact. So now what do we do next? How do we make this solution exact? We find a suitable formula. This is the formula that we're going to use. So when you look at this expression, you say 1 over m, and then dm dy minus dn dx. This is what you're going to have. This is what you're going to have as the expression. And then once you simplify this, you're going to have this as your answer, and it's going to have a negative outside. But remember what I told you, when the function that you found only contains y, meaning when finding the integrating factor, you always have to add a negative outside. So when you add a negative, you say minus and then times this negative there, it will become positive. That's the reason why here in the solution you can see they've just considered it to be positive. Yeah, it's just that simple reason. And then from there you can simplify this. These two will go on top. It will be ln y to the power 2, and then that ln and that e will cancel, and then you get this as your solution. Okay. So now if you multiply, so this solution that you found here is called the integrating factor, and then when you multiply it throughout this equation, you are going to get this equation. So having gotten this equation, you can now test it, and then after testing it, you make sure that dm dy is equal to dn dx, and then you find the general solution. So on this first equation, the way we remember what I said, on this first equation here, you only on m, you only, when finding the general solution on m, you integrate this with respect to x, and then that is what you're going to get when you differentiate it with respect to x. And then in this expression here, which is n, you only integrate the terms that only contains y, the terms that do not contain x. Yeah, so here, meaning we're not going to consider this, we forget about that, we only integrate this part which only contains y, even this part which only contains y, and this is what we're going to have as our solution. Okay, so there's an exercise at the end. You can do it at your own time, and then once you finish or once you do it, you can submit it so that I just check through to see if what you've done is correct or wrong. If you are wrong at some point, I'll correct you just right there, either on WhatsApp, Telegram, or depending on what media you're going to use to call me or to contact me. So thank you very much for watching today's lesson. See you in the next lesson. Shalom, shalom.